Okay. So right now, today we had an elements 31 to 60 quiz, and then we have a quiz tomorrow on powers of 10 and lab equipment, and even the powers of 10 or the powers of 10 metric to metric conversion. All I'm going to do is I'm going to stress scientific notation also. Get that? So we'll go over that again today. And some of the stuff we do today is not on the quiz. Like, remember how you did serial dilutions? I don't have that on there. That'll be on the test. And then we have 61 to 90 on, I said, hey, thanks. That's on video. Okay. Well, anyway, all right, wait a minute, what was that? Oh, yeah, and then Wednesday, since we're not here on Monday, I'll wait till Wednesday to give you the elements 61 to 109. And then we do have a test on Thursday. And I'm going to look in, we should be good. We should be good on that day. And I also like Thursday because on Thursdays, you actually, if you wanted to come in early and you say, I'd like to have a little pressure taken off of me, I'd like to start the test early. You could do that if you want to come in early in the morning. And you also have a break after it, so if you think you want to run a little bit into the break, you can. I don't want time to be an issue. I'm going to try to work on that. I have to be careful. The class is only 45 minutes this year, but I have regularly some tests in this class that are 2-period tests anyway. And so some of the tests are, they're bigger anyway.
3-period.
So what now? Also, I gave you a homework assignment, and you should be working on that. I know you're working on elements, but this is what you need to do, and it tells you how to get full credit for that. I'll probably give you the answer sheet on, maybe I'll give you the answer sheet on Wednesday, and then you can take it home, and the multiple choice thing, you take it like a practice test, and then you just have to grade it. And you don't get a lower score if you didn't do well enough on the practice test, you get it? But you have to show me that was what you tried to do. You tried to take a little practice test. Okay, what do you think? So we're moving a little faster, right? We're okay in that? We have to keep moving, and I know that even though some of the stuff, a lot of stuff right now we've done, we're moving at a little faster pace, and I'm trying to go to a little bit different depth on some of these things too. Do you remember yesterday we were doing this thing right here? And remember this? Now this is a technique that you will use in here, and you probably will use in college, if I had to guess. There are 2 times you might use it. One might be in a microbiology class if you happen to have taking more biology classes. Another one might be if you're doing a lab on spectrophotometry. That's when we'll use it. We'll use it like that. So you would make a stock solution. Do you remember that word? And a stock solution is the starting solution. It's one you know the concentration of. Everybody got that? So the stock solution is not mysterious. This one I happened to go to the grocery store. It said 5% acetic acid. Well, that was my stock solution. You guys will be making these standard solutions in here, but you'll make your own solution. And you just have to be careful enough, make sure it's made right. Otherwise, you mess up your whole experiment, right? So, all right, so then if you were to take one piece of this out and add 9 mils of water to dilute it, then how many pieces are in this tube again? How many milliliters in this tube? 10. And of the 10, only one of the 10 are original, right? So that means it's only 1/10 is concentrated, or the biologists and chemists like to say it's a 10x dilution. It's been diluted 10 times. So if this was 5%, this would be 0.5%. Pretty easy? Okay, next, if you take, and it's called a serial dilution because it's in a series. And if you take 1 mil out here and 9 out here, then it's also, this is 1/10 of that, but this is 1/100th of that. So not 0.5, but 0.05%. And it's called a 10x, 10 squared x dilution. It's been diluted 100 times. Now, I thought you understood that pretty well yesterday. So I'd like to take you in an area where I didn't do this in the 10th grade. I want you to imagine that I have a stock solution, and let's just pretend it's 3 molar. So let's say it's 3 molar HCl. Let me tell you the good news about this is that if you were doing an experiment like with the germinating seeds, like I talked about, here you would have 5 and 0.5, and then 0.05. And you say, look, I think I can find it. I think I can find that place where the seeds germinate as they did in the control. And I can see what is the safe level. I did find this. I knew I knew I had one of these. This is from the city of Greensboro, and they send this to me every year. And if you'll take a look, it'll tell you that on the average, if they were looking for, let's see, how much calcium is in the drinking water, okay? And it says the units are milligrams per liter, okay? Anyway, and it goes over here, it tells you what the average is, like that. And it tells you range. The range is what they, maybe the highest or the lowest they've ever had. Let's see. I don't see. Do you see the acceptable level? Maybe the range. Yeah, they have to be within this range. I think this is the acceptable level, so they want it to be within that range. But they look at things like how much calcium, how much fluoride. They actually put fluorine in the water, don't they? Do you know that? For anti-cavity. So if you have city water, that's why the dentists say, do you have city water? What's that have to do with you looking at my teeth? And they actually know that people who prepare their foods with drinking water, or they might drink it out of the tap, they have a little extra protection against cavities. And that's why cities put that in there on purpose. We have well water, you don't have that extra fluoride treatment, and you tend to get more cavities. Depends how you eat. Eating has everything to do with it also. Okay, so they might look at pH, and they might look at sulfates and things like that. So I just want to show you lead. They look how much lead is in the water. They can't get rid of all the lead. That would be really prohibitive as far as cost. Okay, so I thought I showed you. Now, so let's say you did a 10x dilution, but what if you thought, wow, somewhere between here and here, here's 0.5 and here's 0.05. I think the acceptable level is somewhere between that. Well, how do I get between those? How can I get in between those numbers? And so let's do something like this. What if I take 1 milliliter of this, and I add 4 milliliters of water? Okay, I'm gonna put them in beakers today instead of test tubes. Okay, what is the concentration of this guy? Let's try it. See if you can figure this one out. What would the concentration of this one be? And I'm going to do it again. I'm going to do another one where I take 1 milliliter of this out, and I'm going to add 4 milliliters of water. All right, who wants to try it? Take a chance. Rollins, what do you think? I'm going to see it with you.
Is it 1/5 concentration?
Okay, so here's 1 piece, and here's 4 pieces. There's a total of what, 5 pieces? So this thing should be 1/5 of the concentration of that. Very good. So what would that be then?
5.
All right, 1/5 of what? What was the original concentration?
Oh.
The original was 3 molar. So what is this? What's 1/5 of 3 molar? Uh-oh. Anybody? You know. Like 3 divided by 5? Like 3 times 1/5? What is it?
3 over 5.
Yeah. What's that give you?
Oh no, off the top of my head.
Okay. What is it?
Everybody knows except
What?
80%.
Oh, wait. Okay, so what's 1/5 of 3? How about that? What's 1/5 of 3?
Wait a minute.
Okay, so I think it comes out to be 3 divided by 5, doesn't it? Or isn't that is that right? 3 divided by 5? Isn't that 0.6? Yeah.
Oh, yeah.
Okay, so all right, now let's do this one. Let's do this one. What's the concentration of this one? What's the concentration of this one? All right, Clayton. This is a little hard. Do you have a calculator? Yes. And I like that because notice that this is 1/10, and this is 1/10 squared. This is 1/10 cubed, isn't it? So 1/10, 100th, see that? And so this would be 1/5 squared as concentrated as here, right? It's 1/5 of that, which is 1/5 of that, 1/25. Now that one I have a little trouble in my head. What's 3 divided by 25? Is it going to be 1/5 of that anyway? Is that right? Something like that? So anyway, I want to show you that instead of a 10x dilution, we could call it a 5x serial dilution. See that? Okay, and one more. Let's do one more. Let's start out with a stock solution of, let's do percent. It's 8% salt. So 8% salt, and what if I take 1 milliliter out of here, and I add 1 milliliter of water? Okay, what's the concentration of this one? All right, Jeff. I take 1 mill out of here, and add 1 mill of water. How many total? Huh?
Well, how many milliliters does the first one have?
That doesn't matter. That doesn't matter. So what I'm doing is I'm taking one piece of the original and adding one piece of water. So a total of how many pieces? 2. Of the 2 pieces, how many were original?
1 says 4%.
So 1 of the 2, so it should be half of the concentration. Is that right? Half of that would be 4%. Let's go. Let's do it again. Let's do 1 mill, and let's do 1 mill of water. Okay, and Parker, what's the concentration of this one going to be?
2%. Because,
Dang, you're smart.
yeah,
Okay, so we could say it's 1/2
1/4.
squared, right? Or 1/4, and 1/4 of that would be what? 2%, or you could say it'd be 1/2 of that, either 1/2 of that or 1/4 of that, right? So you see how it works like that? So you could make any kind of dilution you want, depending on what you want to do with your experiment. Okay, again, I wouldn't do that with 10th graders. I did this with 11th grade, as a matter of fact. I waited till your 11th grade to even do this one. So, are you okay on serial dilution? Pretty good? All right, well, let's go over, and we did this, we did scientific notation yesterday, and I want to, let's do real fast. We'll do it again. Let's see where I'm at here. Oh, here. Okay, so you're supposed to say to yourself, I have this down. I'm going to master this, and if I go to college, what if I don't even take chemistry my first year or physics? I'll have it. It's okay. I'll have it the next year. I'm not going to forget how to do these. I really think you should stay away from the 3 rules that put it in and the 3 rules that take it out. The ones you see a lot of times, even in science books and especially in math books. Math books for sure do a very concrete way of doing it because they think if you memorize those steps, you're going to get them right. You say, what's wrong with that? There's no way you're going to memorize those all for the next 3 or 5 years. It's not going to happen. You're going to switch left and right around. Is it left when I put it in? Out? Why do it? Why torture yourself? If I look here, if I look at this number here and I say 1.2 times 10 to the minus 4th, what do I see? What should I see automatically? What kind of number is that? Owen, what do you think? What kind of number is this? 1.2 times 10 to the minus 4th. Right? Just like that, what do you see? Is this one of these numbers that's 1 and bigger, or it's a decimal?
Doesn't it get bigger?
What now?
It gets bigger.
No, what I want to know is what kind of number is 1.2 times 10 to the minus 4th?
minus
Oh, then it gets smaller. It's a tiny.
No, not get. What kind of number is it?
It's a small number. It's a decimal.
It's a decimal. Okay, now, one more time. Now watch. I already know this is a decimal number. And so when I take it out of scientific notation, I have to move the decimal place 4 places. When I get done, I'm going to get a decimal number. So you can start at 1.2 and you say, now move it 4 places. And you say, I need to memorize left or right. No, you don't. Move it both ways, and one of them will make it into a small number. And 1, 2, 3, there we go. See that? I honestly think that's the way. I wish somebody would have taught that to me. I would just I wouldn't have to worry about remember left and right. Now, I'm going to do something a little more advanced than this. Just a little bit. Sometimes you'll do some calculations, and so what if you get something like this? Okay, so what's wrong with that? There's nothing wrong with that number, but it's not really in scientific notation, is it? So why is it not in scientific notation?
Because it's 3,800.
Frozen. Hang on. Okay, okay, sorry. Why is it not in scientific notation?
Because it's too big.
What now?
It's 3,840.
What is too big? This is too big?
No, the one on the left.
Right, and the rules, the quote rules of scientific notation, this part of the number has to be a number between 1 and 10, not counting 10. Does everybody know why I keep saying not counting 10?
Because 10 is.
Who knows that? What? It could be 9.9999999, it just can't be 10. Why can't it be 10?
Because that would be a power.
Say it again?
Because that would be a power.
It would, and there'd be two ways to represent a number, wouldn't it? And they only want one way to represent a number. So anyway, right here, there are two ways of doing this. And I did this last year, you might have forgot, so let's try it again. How do I put this in scientific notation? Well, the first way is the underhand serve with it. Look at this part of the number and put it in the scientific notation. And that's 1, 2, 3, and is it positive 3 or negative 3?
It's positive.
It's big. Positive 3, right?
Yeah.
Now, I can't forget this part here, though, so I got to put that over here. And then when you multiply numbers with exponents, you add the exponents, don't you?
So is it just minus?
Yes.
Everybody get that? Okay, now that's the easy way of doing it. You simply take that number, put it in scientific notation, put that next to it, do like there. The way that probably some of you should be doing it is this way. I have to make that number between 1 and 10. I did. But what did I do to do that? I made this number 1, 2, 3 powers of 10 smaller. Since I made this 3 powers of 10 smaller, I had to pay it back by making this 3 powers of 10 bigger. What's 3 powers of 10 bigger than this? What's 3 powers of 10 bigger than that? See? So we get the same answer, don't we? Anyway, I think you should be able to do that. Can I give you one more and you try it? Let's everybody try this, okay? Now, let's try 0.000612 times 10 to the second. How about that? See if you can put that in scientific notation. 0.000612 times 10 to the second. Put that in scientific notation. And try it both ways, honestly, and you say, I'm more comfortable with this method. I'm more comfortable with this method. Okay, I'm interested in knowing which method you pick. How many of you took the first part of the number and put it in scientific notation? How many of you felt comfortable with that?
Yeah.
Okay, so let's try it that way. Forget that this exists for a minute, and it's going to be 6.12 and times 10 to the 1, 2, 3, 4, and that's a little guy, 10 to the minus 4, and then I got to come back and replace the thing. So the final answer should be 6.12 times 10 to the what? Negative 2. Now let's do it the other way. The other way, I actually can do it like in one step. I don't have to write this down, but that's right. This is going to become 6.12. But how did that little guy become 6.12? How did it became 1, 2, 3? I made this 4 powers of 10 bigger. So I have to make this part 4 powers of 10 smaller to be the same number. And what's 4 powers of 10 smaller than that? What do you think? You feeling comfortable with that? You don't like that one? Okay, so figure out which way you like doing that. And I want you to be so comfortable with scientific notation. You'll never be nothing in science, no metric unit, no scientific number, nothing's going to shy you away. So I'm ready for that. Go ahead. Give me anything you want in scientific notation. All right. Questions on that? You all right? You okay? Okay, so we do you know that in almost every science textbook. You say you're taking AP Physics? I'll bet they had something about measurement in there, didn't they? They did. And even though I do measurement in the 10th and 11th grade, we got to hit it one more time. We're going to hit it one more time. And a measurement is an observation that includes usually a number, doesn't it? And measurements might be something like this. Measurements might be 36.2 centimeters. That's a measurement. Here's one, 0.005 microns. That's a measurement, isn't it? So measurements have, they have three things in common. Do you remember the three things? And this is hard to remember everything, but what do all measurements have in common? They all have a what?
Unit, right?
They're what?
Number units.
A number, and they have a unit. They have a number, they have a unit, and they have what? Let's see if everybody remembers this.
Sig.
It's a word. Did somebody say it? You're right. You have to remember that. Now, if you guys had stats, you're one of the few people in the school that actually do understand that sometimes measured numbers, when you graph them or whatever, you may not draw your graph dot, do you? You know what a linear regression line is, don't you? And so you know that if it's a measured number, that there is error. And so we have to account for that, and stats actually tells you where to draw the line, that kind of stuff there. Whereas if I'm simply counting, if I'm counting numbers, if I count numbers like 3 pencils, there is no error in there's no error in that because it's a counted number, and it's not 3 pencils. Well, it could be 2.99. No. A counting number has no error. We accept 3, the 3 that used in math class. The 3 that's in a counting number is 3.00000 to infinity. It is accepted as being no error. Got that? So when you do a measurement unit, they're going to talk about what measurements are, but then they're going to spend a little time talking about these numbers. Now, where do these numbers come from? Let's see if you can remember that. Where do they? How did you know to write this many numbers here and only write one number here? Where do they come from? And I'll give you a clue.
Your tool of measurement.
There's that. What is it?
The tool of measurement?
Right. The instrument that you use. The instrument they use, the way it's made, and usually how much it costs more to get a better measurement. Got that? So if you go to college, you may run across an instrument which measures something like, we have a balance here that actually measures thousandths of a gram. But I was in college and we had one that went 10,000th of a gram. Now, those kind of balances that measure 10,000ths of a gram, they're in a special room, and it's on usually a marble table. Something has a lot of mass to it. So if there are any little vibrations out there, it won't affect the balance all that much. So anyway, you're going to pay a lot of money for something that goes down to a 10,000th of a gram. You also, I've never seen a balance that goes to 10,000th of a gram that also can measure 100 grams. You're not going to be able to measure 100 grams on the same balance you did 1,000th of a gram. So you might have a limit there, a capacity. Every balance has a capacity. This ruler here, I'm going to use the metric side here. When I pick up a ruler, whether it's an expensive or not expensive ruler, it has limits. And so what I notice is that it has 9 and 10, and it has lines for that. It has lines for the ones place, isn't it? So I'm certain about the ones place because of the lines. Then I see lines in between there, and those are tenths of a centimeter, and that means I can be certain about tenths of centimeters. But then, what do you call the distance between these two lines? What if it's between the two lines? It's not centimeters, it's not a tenth of a centimeter. What area are you into now? Where am I at? What decimal place am I in now? What do you think, Rollins? What's the limit at which I can use this thing? I'm certain about the ones place, like 5 centimeters, 10 centimeters. I'm certain about that. And I also have lines for 1/10 of a centimeter. I'm certain about tenths place. But what am I not certain about? So everybody who's a scientist or an engineer knows that when you measure, you always put down all the certain figures, and you must estimate one uncertain. Yes, remember that? So if I pick up that ruler, I have to have something over here, and I have to have tenths place, and I have to have hundredths. So if you saw 12.45 centimeters, I could measure that with this ruler. I could not measure 12.45. Oh, I think it's a little bit more than halfway there. I think I put point. No, you cannot. You cannot go to thousandths place, because you can only be certain about these, and you must estimate one. And if you put the certain and the one uncertain together, that's when you get this term called significant figures. You get it? I don't know why, but I have several people, they come back and they said, oh, that's significant figure. That's one of the first things they did when I was in my class, my chemistry class, or my physics class, And unfortunately, and I mentioned this to you before, some books make it way, way harder than it should be. It's way harder. Number one, a lot of teachers they play a game. Let's play a game. How many sig figs are in this measurement? Okay. You should tell the people where they come from. It's not a game. It's like they come from the instrument, don't they? That's why you get different amounts of sig figs, because you have different instruments. So let's go this is the page right here. And again, I'm going to do this a little quickly because you've had this before. I think the easiest way to do sig figs is not learn 5 rules. As a matter of fact, one of these rules should be broken up into 2. And I've seen books that says there were 6 rules, there were 7, there were 5. And no wonder a lot of students don't like sig figs, because it's a game and they can't remember all 6 rules. Why don't we keep it simple? Let's keep it really, really simple, all right? And you're not going to miss this. You're not going to miss this. Next year, the year after that, you're not going to miss it. Rule number 1. If you're in a measured number, not a counted number, if you're in a measured number and you're not a 0, you're in. You got it? You're in the club. So let's go over these, and I'm going to put a single line here. I know you're in. All these are significant figures. There's no way that these are not significant. Yes, go ahead.
Don't we have break now?
Don't we have what?
Break.
Yeah, we have. This class ends at 9:50. Yeah, that's it. Okay. All right, I'll say by tomorrow. Listen, tomorrow it's the quiz is only on powers of 10, and then metric to metric conversion, and then I picked like 6 of the pieces of equipment. And I got that. All right, thank you.